Thank you very much. Is this working? Yep. Can you all hear me? Good. Let me close this, because thermal throttling being what it is, my laptop will burst into flames. OK, great. So the title of my talk is The Pathologies of Big Messy Data in Telecoms. It's an obvious nod to an article that was posted on ACMQ several years ago now in 2009 by Adam Jacobs, The Pathologies of Big Data. That article was about dealing with data at scale on massive data sets and the typical problems that you run into there. This talk is more about the problems that I see in my domain, where we're dealing with what I call messy data. So it's data that is not well formed, that has lots of latent errors in it, that typically in the course of the last 10, 15, 20 years in telecoms, those problems have been just latent and not detected, because we haven't had the tools to actually look at this data at scale and find the outliers, find the anomalies. A little bit about me. This is me back in 2001 when I first started my career in telecoms. Well, actually, I started a little bit before that. I was running internet cyber cafes when I was 16 years old and that kind of thing. This is me at the ripe young age of 18 as a senior systems engineer at a major carrier. I don't know why they hired somebody who looks like he was 12 years old. I love this photo because it's got, I'm quite a nostalgic person, as you can probably tell from the He-Man t-shirt. And so, you can see big whopping Sun tape drives, one of the early Java books there. That's a great photo. So your systems have errors. Have we got any Haskell people in the room? Yep. Yours too. None of you write perfect code. The errors may actually not be in your code. They may be in the data or the systems that are feeding the systems that you are running. And in a telco environment, that gets very interesting, because typically you have no control over those other systems. And so you have to put up with what you were given in large part. The data can lie. So in the telco domain, you kind of have two sets of data. You've got inventory data, which is all of those devices in the network, the physical devices, the bits of copper in the ground, even your CPE device, your customer premises equipment at your home that plugs into your router and all of that. And then you have the time series data, which across time, all these systems are generating metrics. And we need to be able to look at that data, because that's how we manage networks. It's how we manage the capacity of the network. It's how we manage the faults on the network. And it's how we predict when things are going to go wrong, or at least, if we can't predict, fix them when they do. We talk about code being data and data being code in some languages, but do we ever actually unit test our data? We don't see that very often, and we don't see that in the telco domain for sure. I'm going to show you some tools today that you can actually use, not just in the telco domain, but fairly generic, to deal with massive scales of data and to find the outliers, find the anomalies. So telecoms is a very strange industry. It's strange because it's very insular and inward-facing. A lot of the innovations that we all take for granted in this room, they don't break into the telco world, because it's made up of the HPs and the IBMs and the big behemoths of industry that wrote their products 15, 20 years ago and don't really have a vested interest in changing them. They're backed on multi-million-dollar vertically scaled Oracle databases. They're just not performant. And you look at the scale of data that Facebook and Twitter and such like are dealing with. Well, we want that in the telco domain. I mean, the telco almost created big data. There is so much data available from all of these network elements. We're talking about hundreds of thousands of logical trunks, millions of customers, tens of thousands of pieces of hardware. There are a few different types of telcos. I specifically work in the assurance domain. Assurance is about assuring the services that the customer is paying for. How many of you here have an internet connection at home? Good company. I bet you think that if you choose ISP A over ISP B, they all look the same internally. They're using the same hardware. They've probably got the same systems. Their inventory all looks the same. couldn't be further from the truth. And in fact, a lot of acquisitions happen in the telco space. So you end up with this very strange amalgamation of different systems that don't talk to each other, and just this accretion of mess, as I call it, over time. These are tools that were made many, many years ago. So the inventory data on the left is from Nagios, which I'm sure some of you know about. Nagios was first written in 1999. The one on the right is Cacti, which was written in 2001. That's 14 years ago. You'd be surprised how many ISPs are still using this software. You really would. And not just small ISPs, big ISPs. Adrian Cockcroft keynoted at the conference, and he said most monitoring tools break when you're working on an infrastructure the size of Netflix. The tools just blow up and can't figure out how to display stuff. You saw in that Nagios screenshot, there's only about 60 devices there. That's pretty much the limit of what you're going to display. That's all but useless to a telecoms operator who has 10 million customers. Tens of thousands of network devices, and a very complex interrelationship between all of those. A couple of years ago, I founded Savvi, and we were working on building out a platform to kind of bring a lot of this innovation into the telecoms sector. And some of the tools we used back then, one of them was Titan, which is a graph database, which some of you may have heard of. It's an open source project. It's extremely scalable, quite pluggable in the backends that you can use. You can use Cassandra, Berkeley DB, etc. But it's all well and good putting the data in there. You've then got to do something with it, right? Now Titan's great because of this gremlin language it has to be able to query that data, but you really want to be able to visualize it at scale. There's a tool called Gephi, which unfortunately is aging a bit now. It never really progressed past version 0.8, although I've been assured for a long time that there's a new version coming. It's a fat client written in Java, but it scales pretty well. It uses OpenGL, and you can display a lot of points, as you can see here. But recently, we've been working with an open source project called Graphistry, or a pseudo open source project called Graphistry. A gentleman by the name of Leo Majerovic, I'm probably completely destroying that name. They're doing some really innovative things with massive scale graph visualization. This uses GPUs on the server side for massive graph layout, and then GPUs and web workers, so WebGL and web workers on the client side to depict large scale graphs. Let me show you what that does to the typical. I'm going to get out of this. Okay, so this is Graphistry. Let me just reload this frame. I'm going to zoom in out a bit as well. So what it's doing here is it dances around. It's actually doing real-time graph layout on the server side using GPUs, and big GPUs, like NVIDIA Titans and such like. And so you end up with this almost very organic-looking visual data set. And this is a synthetic data set, but quite similar in its structure to a typical telco and the scale that they operate at. This is running entirely in the browser, and you can see it is lightning fast. I mean, look at the speed that I can wander around this massive data set and kind of start drilling into the different nodes and things. This is how we should be managing networks in 2015. Not static PNGs generated on the server side, but an actual living diagram of the network that actually connects you to it, makes you feel like you've got your finger on the pulse of what is going on. You can see a lot of structure in this, and you can see how densely connected some of these devices are, the hierarchy of devices, and you can see they've got all sorts of properties relating to those as I scrub over the various things in here. Now, this is a great technology. You can do a lot with this, but how do you get the data in there in the first place? So the nice thing about Graphistry is this is actually coming in from IPython Notebooks. Who here is familiar with IPython? Okay, a few of you. That surprises me. I thought a lot of you would have just discovered this. How many know Python? wow, IPython needs to do a much better job at marketing, or whatever the equivalent is in the open source world. GPython, as it's now called, I hate that name, so I still call it IPython, is a cell-based notebook. So you can see here we've got modules of, or small fragments of Python code, and we can actually iterate through these and run them. So I just hit Shift-Enter on each one, and it goes off and runs that, and then this one. And then I run that. And you can see, once it's executed it, I get whatever my result set is. We're using pandas and NumPy and those kind of modules to work on these massive data sets. And as I go through this, what we're doing is we're actually building up two tables. We're building up a table of nodes, which is this. So we've got an ID for our node, we've got a name for the node, and a bunch of properties. We've also done some things to synthesize like the point size that we want in the graph. So more densely connected devices, we might want a bigger point size. And then we want to do our edges, as they're called in the graph world, so that the links between those nodes. So we do that. And these are our edges. So we have the source and destination node and a bunch of properties relating to that. And then we just call g.plot, and it uploads that data set into the cloud, and Graphistry does their wonderful stuff there, and visualizes it. So this tech actually came out of the security space. You can imagine if you're looking at large-scale botnets or port scans, that kind of thing, these kind of tools are really useful to see the structure in the data. Let me flip back to my presentation. So I talked about this data being messy. What do I mean by that? Well, the data that feeds that notebook is a CSV file. We also often pull it in from Splunk directly and then work with it in the notebook to further refine the data set. When I talk about big, messy data, these are the kind of problems we get. My first talk in Melbourne, I enumerated all of these for the audience, and half of them fell asleep, so I'm not going to do that today. The takeaway from this, there's a lot of problems, right? And you can't solve them all. You literally can't solve them all. They are problems upstream from you. That department doesn't have a budget to fix the problems that you are facing, et cetera, et cetera. Welcome to the world of enterprise. If I just reduce the entries on that previous slide down to this, essentially it's about big and fast data. We're talking about a massive number of network elements, massive number of logical trunks, all with dozens of metrics coming in at an arbitrary granularity. We've got these complex pipelines. They're flaky. You don't control them. A lot of them are batched. You wouldn't believe how many batched interfaces there are where you only get the data every 24 hours. How do you deal with that in a system where problems, alerts, people driving a backhoe through a piece of fiber happen in real time during the day? It's difficult. The data's complex. It has complex relationships between all these devices, and by the nature of it being a network and the OSI stack and layer 2, layer 3 networks, etc., it's multi-layered. And so you might have a problem that you're experiencing at layer 3, in the TCP layer, and it's actually caused by something at the transmission layer. We don't have the tools to really tie all those layers together at the moment. This is a typical box that in Australia, for example, you'll have thousands and thousands of customers going through one of these boxes. It's called a 7450. And the reason I show it to you is just to show you the scale of the data that these boxes have. You can see that it's got a whole bunch of 10 gig e-ports on there. There's an enormous amount of bandwidth goes through one of these boxes. In the SNMP MIBs, who here knows what SNMP is? That's good. But you don't know what IPython is? What's that about? So SNMP, for those of you who didn't put your hand up, Simple Network Management Protocol. I think simple was a bad joke that was made. It's anything but simple in its implementation. One of these boxes has 24,000 things that you could monitor on it. 10,000 of those are counters. Do you know how many a typical ISP monitors? About 12. Right? And they only monitor those 12 on a very wide cadence, usually 15 minutes, 30 minutes in some cases. And so it's kind of small data, but at scale because there's millions of logical circuits on there. So it's a fraction of the data that should really be being used. We're kind of living in this golden age of machine learning at the moment, where we're seeing leaps and bounds in our ability to predict what's going to happen. I'm pretty sure in those 9,605 counters that are available, there are some gems in there that would allow you to predict failures. But we don't monitor them, we don't collect them. And the reason we don't do that is because the systems can't scale. Now, there's a couple of reasons they can't scale. There's a lot of these systems, the management and monitoring systems, even the enterprise ones, all use the UCD SSNMP library that was written back in somewhere between 92 and 95. Couldn't get a clear year on it. It wasn't built for performance. In fact, if you want to see a piece of C code that's got more mallocs, reallocs, and frees than you've ever seen before, go and have a look at this one. It's accreted a lot of cruft over the last 20 years just because of the nature of SNMP being very complex, ironically, and flaky devices with odd implementations. The other reason is that a lot of the enterprise solutions are built on crappy databases. I'm sure I'll get some flack for that, but it's not so much that Oracle's crap. You know, it is performant, it can scale. The trouble is, when you want to scale it, there's a multi-million-dollar price tag attached to that. And so the cost benefit of going and monitoring 9,600 counters every minute of the day for tens of thousands of devices just doesn't make sense. And so they don't even think about doing it. You know, again, a lot of the innovations like Cassandra and InfluxDB and these kind of more performant time series databases have not made their way into telecoms yet. Another problem, I think, is that a lot of the tools that we use in that domain, they're written in Java. Now, I'm not a huge proponent of Java, as anybody who knows me will attest to. Georges Saab, who spoke about Java 9 recently, was saying some great things about how Java's going to get the equivalent of kind of C arrays and ability to do SSE and vectorization across those. That's great. That's kind of targeted for Java 9, I think. But until then, we're building solutions like Spark, which you may have heard in the previous talk that was in this room, on Java, and we're having to do all these machinations of moving stuff off heap and paying this serialization, deserialization tax to move data back and forth. Just feels like we're making life a little bit complicated for ourselves. I've been playing with a lot of columnar stores and such like recently, doing bake-offs between different time series technologies, and I've been doing a lot of investigation into array processing languages, that were very, very old, languages like J and K and Q. I think my wife thinks I'm going through some kind of digital midlife crisis. The performance that you get out of those is, in my experience, 2 orders of magnitude better than what we're getting out of the Cassandras and the Sparks and such like. Right? We're leaving a lot of performance on the table, I think. So this is one of those pipelines that I spoke about. This is just for really one report. You can see, just how many steps there are, different systems that this data is flowing through, all the way from your network elements on the left-hand side of the equation, flowing through element management systems from the vendors, going through data adapters, and of course it's all in XML, right? Which it's lots of voluminous counter data. Why wouldn't you represent it in XML? What could go wrong? These pipelines are really complex, and the trouble is a lot of the things that feed into this, so on the top of this diagram is the inventory data. It's coming from other parties. It's coming from other departments within that organization. And it's messy. It's got schemas where you've got to synthesize compound keys from multiple different fields and regex extractions and things, right? It's not really what SQL was designed for. It's not really what a lot of the ETL tools even were designed for. This pipeline has around 40,000 files an hour that flow through it at the moment. And some of these files are massive. They're like 250 megabyte XML files. It's probably about 100K of usable data in there. We use Splunk to do a lot of our heavy lifting for the data. I won't spend too much time on Splunk. Many of you will have used it yourself as well. There are no magical unicorns in the big data world, unfortunately. But we find it useful because it gives us a single language through which to express all the business logic and ETL-like data flows that we experience in Telco. And it allows us to deal with that messy data in quite an elegant way. It's very easy to do your regex extractions and such like. In fact, I like SPL so much that one of the commands, which was the stats command, I found myself using a lot and wishing that I had it on the Unix command line. You know, as my bio says, I grew up on a steady diet of grep, awk, and sed. And so, you know, I find myself doing a lot of this big data stuff just from the Unix command line. But I kept running into the thing of, oh, I wish I had a stats command. So, of course, as developers do, I wrote one. And you can go and grab it on GitHub. It's not pretty. It was a little, you know, kind of weekend hackathon for me. But I found it really useful because you can, you know, have a look at those CSV files and such like in a different way. And I think we need more and more of those tools. I'm really surprised that the Unix ecosystem of big data tools effectively does not exist, that we never really embraced Unix pipes to the fullest extent. Yes, they had their problems, but I think we've learned a lot over the last 15, 20 years, and they are solvable problems at this point. So I talked about that complex pipeline. One of the things you need to do with complex pipelines is be able to debug them. And so one of the things that we do is we use where have I got it here? We use tools like D3. Does anybody here use D3? It's an awesome JavaScript library by a gentleman called Mike Bostock, who originally worked at the New York Times, left to do other things now. It's a declarative model for working with data in JavaScript and visualizing it, ultimately in SVG, although there are Canvas kind of shims for it. 40,000 files an hour is quite difficult to reason about and get your head around. So what we did is we built this waterfall. I hope we've got Dave. Yeah, Dave's in the room. This probably doesn't like me saying waterfall. You can see the flow of the data across time. So each one of these vertical lines is actually 15 minutes. And for each file, which is on the y-axis, you can actually see the different states that file moves through. And it's interesting because the end state for these files is actually Splunk. And interesting things jump out. You know, if I scroll down here, you'll start to see, like, what the hell happened here? You know, that probably would have been a latent error that had just sat in the system forever because nobody was looking at it at that granularity. The problem here is actually we're putting data into Splunk, but the metadata indexes were not updating. The code for this is actually embedded in the slide on the right. I'm not going to zoom into it, but you can see it's very, very terse. It's a very small amount of code to actually get what is a very useful visualization out of that. So if you're not using D3 in your day-to-day to look at these problems, you definitely should be. One of the problems we have in Telco is also there's no single source of truth. You end up with lots of different departments. There's multiple inventories that actually overlap to a very large degree, but none of them overlap in totality. So we end up using, you know, Venn diagrams and such like to say, well, this is over here, but that's not in there, but it is in there, but that doesn't have that. You know, it's messy. It's messy. So historically, we haven't used the tools to actually go and look at this data and find these. In fact, so Telco is one of the only industries that has a sub-industry that it created to deal with this problem called revenue assurance. So they deal with revenue leakage. You know, they lose money from doing this. You know, these are services that you're billing for that the customer doesn't have, or services the customer has that you're not billing for. And I'm sure you can imagine which one is more important to them. So using things like IPython and being able to ask questions of that data and present them in something that's actually business consumable as well is really useful. Other things we do, you know, because there are multiple sources of truth, again, we use IPython Notebooks to look at that data. So again, you know, the same just cell-based approach to having iterative bits of Python code that you're bolting together, and we get graphs out of it. Now, it's pretty easy to see where you have divergence between two things. So we're comparing actually cacti, which I showed you earlier, and the Splunk data. And you can see, for example, you know, this area, we've got an obvious logic problem. Now, these are usually manifested because of like failover of a link, for example. So the traffic started going down a redundant link and didn't get represented on the screen. It doesn't take much code to actually work with these things. And you know, when we talk about unit tests and such like, I think we should be, we really should be visualizing the results of those tests as well. It will help us get a better handle on how the system is working. Again, IPython Notebooks, sometimes it doesn't have to be sexy. You know, sometimes you can just make a bitmap. This is literally a bitmap of 2,649 circuits in a telco. It's 30 days and almost 8 million data points. It's an enormous amount of data in there. And what it's showing us is the latency of the data arriving. And it's almost damning. You know, you can immediately see that there are problems, or where you've switched from one implementation to another and how that's improved things, or where it's maybe there's a cluster of devices that's got an issue. And we see all sorts of things in the telco domain. There was one I saw several months ago now. It was one of those 7450 pieces of hardware started just spitting out anomalous, massive 64-bit overflow values because of NTP clock drift. Very weird problems that you get in this domain. And again, you know, these are easy to put together in IPython. So you know, don't be scared. So the other thing that you know, these massive graph scale visualizations are useful for is, oh, I gave you a sneak preview there. I shouldn't have done that. Is looking for outliers. So I showed you this graph before. Now the interesting thing about putting this in the hands of the business, of the network engineers, who are actually not as technical as you would think. You know, they can wax lyrical about routing protocols and such like all day long, but they can't write SQL to save their lives. You know, that's not what they do. But you put something like this in front of them, and they start going looking for problems. And you can probably start to see, as I wander around this diagram, some problems in this network. For example, you know, why is this little cluster of things over here not connected to anything else? You end up with these islands of data, fragments of graph just floating off in space. And that, you know, whoever is I spoke about it being different departments responsible for that. If you put that in front of them, it's pretty damning. There's not much they can say to refute that. So you need these, you need this collateral to be able to go and fix those problems and to show the business that it is a real problem. You can use this for any data set. Any data set you can discretize down into nodes and relationships between those nodes, you can use this, right? You know, we talk a lot about, or we've talked a lot about microservices at this conference already, and I'm sure there will be more talks today about microservices. One of the problems we have with that, of course, is that we're going to have many more small moving parts. And we're going to have, also there were talks about Elixir and Phoenix and such like, where you are working with very small, you know, the kind of actor model where you have millions of processes in a single system and then tens of millions across your cluster. We need ways to visualize that, and these are the kind of tools that we can use to do that. So I hope that you will you know, go off and try this tech out and see how it can work for you for the data sets that you work in. So one of the other tools that we use, of course, not everything is a graph. A lot of it is time series data, as I spoke about as well. So when we're looking for these anomalies, we've also started using 3JS, which is a JavaScript-based 3D object rendering engine, basically, for WebGL. So what you can do, scene graph rendering, sorry, that's what I meant to say. What you can do is you can, you know, create a 3D plane in space, and you can, obviously, you know, I mean, people have written games out of this kind of stuff and things. We're using it for a slightly simpler tool, which is to depict massive scales of data. So this is the top-down view. The x-axis is time. The y-axis is every virtual circuit in the state of Victoria. And if I pivot it on its axis, and bearing in mind this is all just running in the browser, you can then see the ebb and flow of the time series data throughout the day. And interesting things jump out from this immediately. You can see the saturation of certain links when they plateau here. The yellow on the top is where there was data loss from the element management systems and such like that feed that data in. It helps you get a handle on that massive data set and understand where the problems are and what the kind of locality of the problem is. Is it likely to be something systemic, or is it something that's just the state of a small neighborhood, for example, or a particular device? These are really useful tools. So we really liked this, and then we thought, this would be a brilliant way to actually depict large scales of data. So we kept working on it and stepped away from 3JS, started to do more on the GPU with vertex shaders and pixel shaders. It's not that difficult. You're writing small kernels of pixel and such like manipulations. And so we took it to the next level, which is, let me show you this. Oh, not that one. This one. This is definitely a laptop melter. So this one is 4 million data points in the browser, a similar size data set really in terms of the source, but we didn't have to reduce it because of the performance of it. You can see like almost immediately the patterns jump out at you from this data. And this is running in JavaScript. If you'd have told me 5 years ago we'd have been able to depict visualizations like this in the browser, I would not have believed you. And we can do a number of things with this, so we can go and filter different colors and change the alpha of them. You can even see, for example, test circuits. So I don't know if you can see the kind of almost, not sine wave, but the kind of logic wave going across there. Those are test circuits generating synthetic data. So these kind of things, it's really useful to get a handle on how is the network working. What's the finger on the pulse, the 50,000-foot view of the entire network? Some years ago now, Shyam Sankar from Palantir coined the term human-computer symbiosis. Now, I've been in the telecoms industry for a long time now, probably in a commercial setting about 13 years ago. I was working on next-generation network management systems at the time. And they were all about root cause analysis and trying to build graph of the network, and therefore you could reason about it. And they had these expert systems, which was the form of AI before we actually knew what we were doing back then. The trouble is, I think for the last decade in the telco world, the vendors have been trying to approach it from an algorithmic point of view. What they've forgotten is that the best pattern matching system, machine on the planet is, anybody want to take a guess? Up here, right? We just need the information put in front of us in the right way, and we can deal with enormously dense visualizations, right? In time, once you get used to those visualizations, you get used to the patterns, and the problems jump out at you. So, we're trying to bring together a kind of suite of those tools to bring that to the telco space. But I think it's not just about telecoms and networks. I think we're going to need that in this very microservice heavy world, this very large scale world that we're working in. The current management tools, they don't work for the scale that we're operating at. We need to be able to collect more data. We need to be able to have the system reason about it and bubble up the problems to us. And then we need to be able to put that information in front of the human operators in the most intuitive way possible for them. These new tools, especially those that are generic in their application, they open up a ton of new possibilities for how we can manage networks and data moving forwards. And that's the end of my talk. Thank you for listening. And if anybody has, do I have time for questions?
We do indeed. Yes.
Great.